I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on work, heat, and internal energy and how to calculate those values. In this video, we're going to talk about work, heat, and internal energy and how to calculate each of those values. We're going to start with work. So we look at the first law of thermodynamics. We know that work is the mechanical work that's kinetic or potential energy that's transferred into or out of the system, usually through the piston that's moving. So in the last video, we learned that work is equal to the negative pressure times the change in volume. That's a constant pressure or an isobaric process. So if we draw an isobaric process on our PV diagram going from A to B, again, don't forget to draw the arrows on your PV diagram. What we learned in the last video is we can calculate using the equation, work is equal to negative pressure times the change in volume, or we can find the area underneath that curve. Now, the problem with the area is we have to determine if that area is positive or negative based on what's happening with the volume. So with this case, with the volume expanding, that means that we've got a positive value for our change in volume, which means that our work done by that process from A to B, that isobaric process, is going to be negative. So the system's energy is decreasing. When we switch it around and we go from B to A, we end up with work is equal to the negative pressure times the change in volume, which is a negative number. So we get two negatives, and that's going to give us a positive. So the work is positive when the PV diagram goes from right to left as an isobaric process. Now we can also look at from B to D, and we can calculate the work done from B to D. Well, remember, work done is negative pressure times change in volume. The volume's constant as well, so that gives us a work done that is zero. So when we have an isochoric process, or the volume not changing, that means the work done is going to be zero. If we look at the overall process from A to B to D, that's the work that's done is just the area underneath the curve. And then if we take that process from D back to C, we have another additional work that's done from D to C. Now the total work is just going to be the sum of the two works from A to B to D and from D to C. If we look a little further, the work from A to B to D, since it's an isobaric expansion, we know that the volume increases, so that means that that work value is going to be negative. So we have a negative work for A to B to D. Now from D to C, we have an isobaric compression, which means that that work value is going to be positive. So we're going to add that work together. So we know overall the work is going to be negative because we have a larger area from A to B to D. But the total area is just going to be the rectangle of ABDC. We can find that, and that we know that value is going to be negative because the work from A to B is larger than the work from D to C, and A to B is negative. So we can use the equation, the negative of the difference in the pressures times the difference in the volumes, and that's going to give us an overall work that is negative for this process that takes us from A to B to D and then back to C. So let's talk about calculating heat. So heat is Q, and remember that heat is an energy transfer between a system, the container of gas, and its environment. The cause of the energy transfer is the temperature difference. And the key here is remember that heat is an energy transfer. It is not a property of matter. So if heat is an energy transfer and we have a warmer surrounding and the cooler gas inside the container, that means there's going to be heat that is transferred from the outside going into the substance. And what that does is warms the gas up and it transfers heat. So therefore we end up with a warmer gas until the system reaches thermal equilibrium. Now, if the reverse is true, then the energy comes out and the Q value is going to be negative because the gas is now losing heat as it's transferring it to the surrounding. And a side note that the energy transfer to the cold via heating is equal to the negative amount that is lost from the hot. Remember, energy through heat travels from hot to cold. So let's talk about specific heat and what specific heat is. A specific heat is a constant value for individual substances. It's not a measurement of heat. So the specific heat for an individual substance is defined as the amount of energy in joules required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin, since the temperature change is going to be the same in Celsius or Kelvin. Each substance has a different value. So for example, liquid water has 4,186 joules of energy required to raise 1 kilogram of water 1 degree Celsius. So that's the constant value for liquid water. And it'd be different for ice and it'd be different for steam. And so it is different for all substances. So this is what specific heat is. And the symbol is a lowercase c, and the unit is joule per kilogram degree Celsius. So if we know that specific heat is the amount of energy, which is heat, that is required per kilogram of mass or per mass per degree Celsius, that's going to give us this equation as C is equal to Q divided by M times delta T. And if we rearrange that equation, we get an equation for heat, that Q is equal to MC delta T. So we can calculate a heat transfer based on how much the gas's temperature increases or decreases. So Q, and this is the quantity of energy transfer, that's the heating process, and that quantity is going to be measured in joules. Mass of the substance is in kilograms. C, as we talked about already, is the specific heat of the substance. That's joules per kilogram degree Celsius. And delta T is the change in temperature of the substance in which the heat is transferred in or out. That would be the gas in the system. And that's in degrees Celsius or Kelvin, that change in temperature. So the units for heat, we know the SI unit for heat is joules, but there's also other values. So a calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. That's the definition of a calorie. So 1 calorie is equivalent to 4.186 joules of energy. Now we also have a British thermal unit, BTU, which is the amount of energy required to raise 1 pound of water by 1 degree Fahrenheit. Of course, these are just side notes. We're going to use joules as our SI unit, but it's good to know what a calorie in a BTU is. 1 BTU is 1055.06 joules. And a side note that a calorie with a capital C is actually a kilocalorie. That's the unit of measurement in the foods that we consume when you see it on the labels for your food. So now let's transition to internal energy. We've talked about heat and work. So internal energy. And internal energy, remember, is the energy of the atoms of the molecules of a system or the gas. In this case, we're looking at a monatomic ideal gas, which means that the molecules have all translational motion, which means it's just kinetic energy of the particles. It's directly related to the temperature of the gas. The higher the temperature, the faster the particles move, the more energy the particles have. So we can calculate the energy of an individual particle by using the kinetic energy equation and finding the average of all of them, because they're not all going to have the same speed, but the average kinetic energy would be 1/2 m times the v squared average. Now, it's the average of all of them, but 1/2 m is going to be a constant. So if we average all the 1/2 masses, it's going to be the same. But the average of the square velocities, if we take the square root of that value, this is known as the root mean square velocity. And this is what's used to calculate the kinetic energy of particles. So the root mean square, we just kind of do the backwards of what it says. You square all the velocity values, then you average them, and then you take the square root of that, and that is the root mean square velocity. And the reason we use that is because in our kinetic energy equation, we're squaring the velocity. So that is going to be our RMS. Now, there's a long derivation that we could go through, but I decided we're just going to use this equation to calculate the average kinetic energy of a particle is 3/2 the Boltzmann constant times the temperature, which is a little bit easier to find the internal energy of one particle using the Boltzmann constant. So if we use that equation and we solve and we divide by mass, the 1/2 would cancel out, and then we take the square root of each side, we end up getting the VRMS is the square root of 3 kBT divided by m. We could take kb divided by m, and then if we multiply that by Avogadro's number on the top and the bottom, well, we know that kb times Avogadro's number, well, that's the universal gas constant, R. And the m value is the mass of an individual molecule, so multiplying by the Avogadro's number gives us the molar mass of that substance, and those would be found on the periodic table. So we can substitute Kb over m as R over m, so that gives us this value, square root of 3RT divided by the molar mass, and that's how we could calculate the VRMS, is just knowing the temperature and using those two constants of the universal gas constant and the constant from the periodic table of the molar mass of the substance. So that would be a lot easier than actually trying to measure individual values of individual particles. So if we look at the internal energy for equation for one particle and what each value means, the VRMS is the root mean square velocity. Remember, we're using that because in the kinetic energy equation, all the velocity values are squared. So we take the square of each individual velocity value, then we take the average, then the square root. Kb is the Boltzmann constant, T is the temperature, and that's measured in Kelvin, and m is the mass of one molecule of gas in kilograms. R is the ideal gas law constant or universal gas law constant, and m is the molar mass, and that's in kilograms per mole. Kilograms per mole is important because the numbers on the periodic table are in grams per mole. So the internal energy for a sample of gas for one particle we know is 3/2 kb times T. But for an overall gas sample, well, we can find the end of one particle. If we multiply by all the particle numbers, which is capital N, that's going to give us the total internal energy of the gas. So we can calculate the total internal energy of the gas if we know how many particles and we know the temperature. That's going to give us the internal energy. But again, we know that this NKB from our ideal gas law is equal to N times R, N being the number of moles. So we can also calculate the internal energy by doing 3/2 nRT, which is probably a little bit easier because it's easier to know the number of moles than it is the number of particles. So both of these equations are equivalent and both are on your formula sheet. So both of these can be used to calculate the total internal energy of a gas, where U is the internal energy measured in joules, and capital N being the number of gas molecules. Kb is the Boltzmann constant. T is the temperature of the gas, and that's in Kelvin. N is the number of moles of the gas, and R is the ideal gas law constant. Now we're going to look at something called Maxwell-Boltzmann distribution. And what a Maxwell-Boltzmann distribution is, it graphs the number of molecules on the y-axis versus the speed of the molecules. And a Maxwell-Boltzmann distribution curve looks like this. And this peak value right here, this is the most probable speed you're going to find a value of a particle. Is most of the particles, if we're graphing number of molecules, that's going to be the highest point, is the largest value of particles have that speed. But the average speed is going to be shifted just to the right. Well, why is the average to the right? Well, the area under the curve is the total number of molecules. And if we look at the areas underneath the beginning and the end, we can see that the triangle at the end is a little bit bigger than the triangle at the beginning because we've got particles that have zero velocity down at the end, or some that don't have any velocity. So that area at the end is bigger, so there's more particles that have higher speeds, so the average is going to be shifted over to the right. Now the VRMS value is going to be shifted just a little bit more to the right from the average. So that's the root mean square speed of the particles. And why is that shifted over? Well, if we take the average of any two numbers or any set of numbers, so 8 and 10, the average is 9, but 8 squared plus 100 squared, well, that's going to give us 164. The average of that would be 82, and the square root of that is a little bit bigger than 9. So you're going to always get a larger value for the root mean square. All right, so the root mean square speed is represented by this line, and if the further to the right that is, means the higher the temperature of the sample of gas in the container. The further to the left means the cooler the temperature of the gas. So obviously, the faster the particles are moving, the hotter it's going to be. The slower they're moving, the lower the temperature is going to be. So let's compare some Maxwell-Boltzmann distributions. So we have 3 samples of gas, and all the containers have the same number of molecules or the same area underneath the curve. So the question we're going to be asked is, which gas has the highest temperature? And what we're going to do is we're going to mark the VRMS on each of those curves with a vertical dashed line. And we remember that the further to the right means the higher the temperature of the gas. So the peak of the curve has nothing to do with the temperature. The VRMS is solely what tells us the temperature of the gas. So more particles having higher speeds means it's going to be a hotter gas. So we mark the VRMS on each of them. And why does the VRMS tell us the temperature and how that's related? Well, if we look at this equation, the VRMS is equal to the square root of 3RT divided by the molar mass. Well, comparing the VRMS to the temperature, we can see they're both in the numerator. So that means as one goes up, the other is going to go up. They're not a direct relationship, but if temperature is going to increase, that means the VRMS has to increase as well. So let's recap work, heat, and internal energy and how to calculate each of those values. So with work, we learned that work is equal to the negative pressure times the change in volume. It's the area underneath a PV diagram. And remember, if the volume increases, then work is negative on the gas. And if the volume decreases, work is positive on the gas. Now heat we learned we can calculate by Q is equal to M times C times delta T, where C is the specific heat of a substance, and heat energy is transferred from hot to cold. It's positive if the gas temperature increases, it's negative if the gas temperature decreases. And then we learned about calculating the change in internal energy with these two equations. And the equations will calculate the internal energy at one point, and then the difference would just be the difference of those 2 points to calculate delta U. So these are how you calculate each of the individual values using the first law of thermodynamics. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.